So what I'm going to do is I'm going to pause it now, start it, because now we're going into microgravity experiment design. So let me ask a question of you. Ladies and gentlemen, there is one variable that plays a critical role in virtually anything we want to study, but it's often taken for granted. Does anybody know what that variable might be?
Gravity.
Grace says gravity. Anybody else?
Pressure.
Atmosphere.
Well, atmosphere is not taken for granted in the sense that you gotta know what your atmosphere is. I understand because you can't see it and it's everywhere, and I understand what you're saying. But when you're doing a controlled experiment, you're trying to understand what the atmospheric composition is, the temperature of the atmosphere. So atmosphere, it's a good thought. I understand where it came from. But Grace said gravity. Anybody else have any ideas? Let me say it again. In given all of the variables that you can change, okay, there is one that plays a critical role in virtually anything we want to study, but we often take it for granted. Anybody have any ideas?
Oxygen.
I'm sorry?
Oxygen.
Oxygen, well, that's part of the atmosphere. Well, I guess I'm leading you down a dead end because Grace is right. Okay? Yes, gravity plays a critical role in virtually anything we want to study. Okay, see, I'm on a rolly chair. You see this? You see that? I'm on a rolly chair. And it's like, a rolly chair comes in handy when you want to put an emotional exclamation point on something. At least I think a rolly chair does that. Sometimes you see cinematographers, they roll the camera out when all of a sudden somebody gets this understanding of stuff. Okay, I'm digressing. Too much coffee. Here's the point. Even a germinating seed knows about gravity because when it germinates, the roots go down and the shoots go up. It's called geotropism. Here's the moment. Whoa. Your body knows about gravity in myriad ways. I'll give you one example. Every time you take a step, your bones are compressed under your own weight. And it sends a bioelectrical signal to your body saying, hey, bones are important. Keep making those bones. But in a weightless environment, well, there is no bone compression because there's apparently no weight, which means the signal to your body is, hey, we don't need the skeleton anymore. You can go ahead and excrete it. And if anybody has ever watched years ago the movie WALL-E, it's sort of like a theme in the movie WALL-E, okay? So astronauts have to work with straps and springs to compress their bodies to force that signal so they minimize bone decalcification. Gravity plays a role in virtually everything. Biology behaves differently if you change gravity. And so here's my question, all right? If I want to understand a particular flavor of essential question, here's the flavor of essential question that drives all microgravity experiment design. What is the role of gravity in that or this or that thing there? That's what the essential question is. What is the role of gravity in this, that, or that thing over there? Well, if that's the essential question, what do you need to change? What needs to be the independent variable?
Gravity.
It's got to be gravity, right? If I want to understand the role of a particular variable, I have to change that variable and see what happens. So I need to change the force of gravity. I have a problem, and I'm going to use my rolly chair again. Here's the problem. There is no way to change the force of gravity because of this. The force of gravity exerted on you by all of the mass of planet Earth. So what I'm saying here is, let me just say it this way. Any two objects in the universe we know will attract each other with a force of gravity. Why? It just is. Any two masses in the universe will attract each other with a force of gravity, but it's a really, really weak force. For you to see gravity, you need to have at least one of the masses truly massive. Okay? If one of the masses is really massive, all of a sudden you start seeing the effects of gravity. Give me an example of two masses where at least one is big and massive.
Jupiter and meteorites surrounding it.
Yes, Jupiter and meteorites, but how about one closer to home that allows you to see what I'm talking about every second of every day?
The moon.
The Earth and the Moon.
The Earth and the Moon, well, yeah, okay. So it took the human race thousands of years to figure out where the tides came from, and we had to wait for Isaac Newton to be around. But what about looking at gravity right now?
Is it the sun with all of the planets?
Okay, let me, well, yes, okay, those are good examples, but I'm trying to get one that's very personal to you. Right now, I'll give you a hint. Right now, every one of you right now is depending on gravity for us to have this video conference. Or you'll be floating away. Anybody? Give me an example of two masses where one is massive and the gravity that is resulting from that is something that you depend on every second of your day.
The Earth and us.
The Earth and
Us in general.
you. Yes, the Earth and you. One of the objects is truly massive, and I'll tell you where you are. Here's Florida. You're sitting in a chair right now watching me from right there. And all of the mass of planet Earth, all of the mass, all of the oceans, the mountains, the continents, the crust, the core, the mantle, the mass of the Earth, 12,000 kilometers, 8,000 miles away from you on the opposite side of the planet. The entire mass of the Earth is pulling down on you with a force of gravity we call your
weight. Body weight.
weight. Your weight is the force of gravity exerted by all of planet Earth on you. And it must be a weak force because it took the entire planet to pull down on you with a force of, well, if you weigh 150 pounds, 150 pounds of force. Is everybody with me on that? Give me a thumbs up if you're with me on that. What do you think happens to gravity when you move the masses away from each other?
It decreases.
Yeah, intuitively, we kind of feel like, well, yeah, the farther away the masses are, the less they know of each other, so gravity kind of diminishes. So, does anybody have an idea of how we can change the force of gravity? Because, right, we want to change gravity to see what happens. That's what we're going for. We want to understand the role of gravity in something we're studying. Anybody have any ideas?
The use of satellites.
And why would you do that?
Gravity is much weaker the further we are from the Earth.
So, very good. So what you're saying is if we move our experiment farther from the Earth, gravity will weaken. And so the experiment will operate in a lower gravity environment. But Grace, what else do you need?
I'm not really sure.
Okay. So I can't remember who said this, but who said that satellites?
I did.
Okay, is it Esteban?
It is.
Okay, so Esteban said, well, why don't we move the experiment farther from the Earth because gravity will get lessen, it will lessen. And so if we run the experiment out in space, it's a lower gravity. And Grace, do you have any idea what else we need?
Zero gravity?
Well, okay, but think about control.
Oh, do we need to do the experiment on Earth as well?
Yes, we need the same experiment done on the surface of the Earth in gravity. So when the flight experiment comes back and we put them side by side, this one operated in a lower gravity, this one operated in Earth gravity. So we've effectively changed the gravity variable, and we can understand the role of gravity by comparing the behaviors. Does everybody understand that? Okay, there's a problem. What is the tallest mountain on Earth? Is it, by the way, is everybody with me on this story so far? Anybody want me to go over anything again? Remember, this is all being taped. Okay, so there's a problem. What's the tallest mountain on Earth?
Everest.
Everest. Not tall enough. I need a mountain 47 times higher than Mount Everest, because that's a cool mountain. If I go to the top of a mountain 47 times higher than Mount Everest, I'm 250 miles above the surface of the Earth. Does anybody want to guess what I might find up there?
A lot of snow.
Less
Well,
air.
there's something else that's kind of relevant to this program.
The International Space Station.
The International Space Station orbits 250 miles above the surface of the Earth. So when I go to the top of my mountain, I'm at the same altitude above the surface of the Earth as the astronauts themselves. I can see the International Space Station fly right by my face, right? And so inside the International Space Station, what is the environment like for the astronauts? What when you see videos, have you seen videos of astronauts in the International Space Station on the space shuttle?
Yep.
What are they doing?
Floating around.
They're floating around. We call that a what kind of environment? Anybody know the word?
Microgravity.
Well, there's a more colloquial word than that. What do we call astronauts that are floating around? They're experiencing
Weightlessness.
weightlessness. Why do we call it weightlessness?
Because they don't have the effect of gravity pulling down on them.
Because there seems to be no gravity there, right? Let me say it again. When you watch astronaut videos, you see them floating around. There's no up, there's no down. We call that weightlessness because it seems like they don't have any weight because there's no gravity there. And let me just define this. A microgravity experiment is an experiment in a weightless environment. Microgravity means weightlessness. Is everybody with me on that? That demystifies a little bit what a microgravity experiment is. So here's my question. I'm standing on the top of my mountain, and I bring my trusty bathroom scale with me. And I put it down on top of the mountain, and I stand on the bathroom scale, and ladies and gentlemen, what do you think I weigh? I'm at the same altitude as the astronauts in space. I just saw them glide by my face really fast. I look through the big window called the cupola, and I'm seeing the astronauts floating around in the International Space Station. And I stand on my bathroom scale on the same altitude as the astronauts above the surface of the Earth. What do you think I weigh?
0.
The same.
You might think I weigh 0 because the astronauts seem to weigh 0. Anybody else want to guess?
Whatever your mass is without gravity.
Well, okay, yes, my mass is the same, but the force of gravity exerted on me, my weight is being measured by the scale, not my mass. So what do you think I weigh when I look down on my scale? Turns out I weigh almost the same as what I weigh in my bathroom on the surface of the Earth. Almost the same. And so let's explain this. What's the diameter of the Earth?
11,000 kilometers.
Well, that's a little big. The diameter of the Earth is 8,000 miles or 12,000 kilometers. So is the International, and how high above the Earth is the International Space Station?
250 miles.
250 miles. So is it out here?
It's like right above the
The Earth is
surface.
8,000 miles across. So where's the International Space Station?
Just off the surface.
It's like over here, right? 250 miles above an 8,000 mile diameter ball is like skimming above the atmosphere. Have they gone very far from the Earth?
No.
No. So would you say the force of gravity exerted by Earth on them, their weight is almost the same as what they weigh on the surface of the Earth?
Yes.
Yeah, absolutely. They haven't moved very far from the Earth. That's why I weigh 90% of what I weigh on the surface of the Earth, which means that the astronauts also weigh 90% of what they weigh on the surface of the Earth, because they're at the same distance from the Earth as me on top of my mountain. By the way, all of this is written up on the website. I know because I wrote it. Okay.
Aren't they just constantly falling and it's more the direction that the gravity is applied to? That is what
No,
causes
the
them.
force of gravity is exerted between centers of mass. So the top of the mountain to the Earth center is the same direction as the astronauts to Earth center when the astronauts are flying by my face. There's no distinction between me and the astronauts. We're both at the same distance from the surface of the Earth. So the force of gravity exerted by Earth on them, their weight is almost the same as what they weigh on the surface of the Earth. They are weighted. They're not weightless. They're weighted. So what's the problem?
Our experiments are supposed to be done in microgravity, but we can't do that if where we're sending it has gravity.
Okay, but it turns out that the astronauts do appear weightless. So we can put the experiment on the International Space Station because it appears as if gravity doesn't exist there. So what's the problem? What are you wrestling with in terms of what we're talking about here?
The math?
Things
Sort
in,
of.
things in free fall are like
Ah,
not really subject to gravity.
okay.
So
All right, so let's go there. So here is the problem. The force of gravity exerted on the astronauts is almost the same as the force of gravity exerted by them on the surface of the Earth. Their weight is the same, almost the same, 90%. They're not weightless, they're weighted. I'm standing on my mountain and I'm weighing 90% of what I weigh on the surface of the Earth. And here are the astronauts at the same distance from the Earth and they're floating around as if there's no gravity. And I don't understand what the heck is going on. So I have to take you to my favorite building because I grew up in the Bronx in New York. And my favorite building is the Empire State Building. So I'm going to go to the 104th floor of the Empire State Building where the observation deck is. And by the way, is the Empire State Building a big structure on the surface of the Earth? It's a tiny little thing compared to Mount Everest, certainly really small compared to a mountain 47 times Mount Everest. Now, I'm in the elevator. There are no windows in the elevator. And I go to the 104th floor and I bring my trusty bathroom scale. And also in the elevator, again, all this is on the website, I bring a little chair from a pre-kindergarten classroom. And what's nice about this chair is when I stand on it, I'm a foot above the floor. So I'm in the elevator. I put my chair on the floor of the elevator. I put my bathroom scale in front of the chair, and I stand on the chair, and I'm going to walk down on the bathroom scale. So I'm at the 104th floor. The doors are open. The elevator's not moving. It's as if I'm part of the 104th floor. I'm seeing people walking around on the observation deck. And I step down from a foot above the floor on my chair on the bathroom scale. And what do I weigh?
Do you wait a
you're
little
gonna
bit?
weigh, you're gonna weigh less than if you were on the ground floor, but you're still going to weigh basically the same, and you won't be able to tell with this like a bathroom scale.
Exactly, Jacob. So I'm going to weigh a little tiny bit less than on the surface of the Earth, but because the Empire State Building is a tiny little structure, you're not even going to see that on the bathroom scale. So what Jacob is saying is when I step down on my bathroom scale, even though I'm on the 104th floor of this tiny little building, I'm going to weigh the same as what I weigh in my bathroom. Everybody with me on that? Now I'm going to do the experiment over again because scientists believe in reproducibility. So I'm going to get back on my chair. And the moment I'm walking off the chair, the moment I'm stepping off the chair to go down to my bathroom scale, something bad happens. The door closes and somebody cuts the cable holding the elevator. What happens to the elevator? Okay, so April says it falls. And what can you tell me about this? What's causing it to fall, by the way?
Gravity.
Gravity. And what do we call the force of gravity on the elevator?
Shit.
Acceleration.
What do we call the force of gravity exerted by Earth on the elevator?
G-force.
Acceleration due to gravity.
Okay, it's not a complicated question. It's the elevator's weight. Oh, right? As soon as you cut the cable, gravity exerted by Earth on the elevator causes it to fall. The force of gravity exerted on the elevator is called the elevator's weight. It is falling under its own weight. And what happens to the speed, April?
It remains constant at a point.
Okay, so what was the speed the moment the cord was cut, the elevator, the cable was cut?
It was slower.
Well, it started from rest, so the moment the cable was cut, it was 0 speed.
Oh, okay, yes.
And then what happens?
It speeds up. Oh, it continually speeds up.
Oh, April's got
Sorry.
it right. It starts to continually speed up. And what do we call it when something speeds up?
Acceleration.
It's accelerating. And what is causing the acceleration?
Gravity.
The force of gravity exerted on the elevator, me, the bathroom scale, and the chair. We're falling. And does anybody know what the number is for the acceleration due to gravity?
9.81 meters per second squared.
Who said that?
That was me. Kenneth.
Okay, so Kenneth said the acceleration due to gravity is 9.8 meters per second, and we memorized that number. But Kenneth, can you tell me what that means?
So that for every for every 9.8 meters, you're accelerating at 9.8 meters per second for every second. So
Okay.
in 2 seconds, you'll hit 19 point.
Okay, so what Kenneth is saying is every second your speed increases by 9.8 meters per second. I don't know what that means. I need to build a bridge to the familiar so I can understand what the acceleration due to gravity is. Well, let me do it this way. Everybody drives, I suspect, or goes in a bus or takes public transportation. So you know what miles per hour feels like, right? The acceleration due to gravity is an increase in speed of 20 miles an hour every second. Every second, your speed increases 20 miles an hour. So after 1 second, how fast are you moving?
20 miles an hour.
After 10 seconds, how fast are you moving?
200.
200 miles an hour. After 100 seconds, how fast are you moving?
2,000.
2,000 miles an hour. After 10 seconds, you're moving 200 miles an hour. You're going to go splat, but if it's a really tall shaft, you don't have to worry about that, okay? So that's the acceleration due to gravity. And let me ask this. Does the elevator car, me, the bathroom scale, and the chair all come down with the same acceleration? Are they all accelerating the same?
Yes.
Okay, if you don't think that, okay, go look up on YouTube a video of an Apollo astronaut dropping a hammer and a feather from the same height on the moon at the same time, and the feather and the hammer hit the ground at the same time. Why can't you do that on Earth?
Air resistance.
Air resistance.
Air resistance. So the moon has no atmosphere. So if you drop two masses, a feather and a hammer from the same height at the same time, they're going to hit the ground at the same time. But what can you tell me about what fills the elevator shaft?
Air.
Air. And what will the air do?
It'll be
Compressed.
displaced as the.
It'll compress and it will cause a
Resistance?
resistance, a drag force. So let me give you an example. You want to go parachuting and you jump out of a plane, and for the first couple of seconds, you're accelerating at 20 miles an hour, increase in speed every second. But the air resistance depends on the speed. The bigger the speed, the bigger the air resistance. And so the air says, no, 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 and it slows your acceleration down until finally the drag force due to the air, the resistance of the air, does not allow you to go any faster. Does anybody know what we call that? Jumping out of
Terminal
an
velocity.
airplane? Terminal velocity, which is about 100 miles an hour for a human being. Well, you can't survive hitting the ground at 100 miles an hour. So you do something smart. You deploy a parachute, which increases the air drag so that you can slowly descend to the surface and parachute another day. Everybody got that? So what we're going to do is we're going to suck all the air out of the elevator shaft, so there's no air resistance. And as the car goes down, we're going to make sure there's no friction between the sidewalls of the car and the shaft. And so now, if we take away all friction, there's no rubbing of the car against the shaft, there's no air in the shaft. What then is the only force acting on the elevator, me, the bathroom scale, and the chair?
An
Gravity.
acceleration of 9.81 meters per second.
I'm sorry?
An acceleration of 9.81 meters per second, or
Yeah.
gravity.
So if we take the air out, so there's no air resistance, so there's no rubbing of the car against the sidewalls of the shaft. Once I cut the cable, the only force acting on the elevator, me, the chair, and the bathroom scale is the force of gravity. We are all falling under our own weight. What do we call that kind of falling?
Free fall.
Free fall. The force, if only the force of gravity is acting on something, we call that free fall. It is free of all other forces except gravity. Everybody understand that? So here's the deal, okay? And once you get this concept, you never have to go back to this storyline again to do microgravity experiment design. But you need to understand what's going on from a physics vantage point. So here's the deal. I get back on my chair to do the experiment over again. The door is closed behind me. I don't see that happen. I'm going to walk back down. I'm going to step down on the bathroom scale from my chair, just like I did before. But the moment I'm walking off my chair, somebody cuts the cable, and all of a sudden, me, the bathroom scale, the chair, and the elevator itself are plummeting at an ever-increasing speed, increasing our speed 20 miles an hour every second. We are in free fall. Okay, here's the deal. Everybody with me on that? Everybody good with that? Okay, so here's the deal. If Jeff moves down 10 meters in a certain period of time, will the elevator's floor move down 10 meters in the same period of time? Let me say it again. As soon as the cable is cut, everything is in free fall. Everything is accelerating down together at 20 miles an hour, increasing every second. So I'm on my chair, a foot above the floor. When the cable is cut, I'm walking off my chair. And so here's my question. If I move down 10 meters in a certain period of time, will the elevator's floor also move down 10 meters in the same amount of time?
Yes.
Anybody else?
Say no.
I say
Okay,
no.
so everything is the hammer and the feather. If you drop them from the same height, they'll hit the ground at the same time if there's no atmospheric drag. Okay, so as soon as the elevator cable is cut, I am 1 foot above the floor. I've stepped off and I'm thinking I'm going to step down on the bathroom scale. As soon as that cable is cut, the elevator, me, the bathroom scale, and the chair start to accelerate down together. So in a certain period of time, if I move down 10 meters due to that acceleration, will the elevator's floor move down 10 meters in the same amount of time?
Yes.
How many people say yes? Give me a thumbs up. How many people say I'm not sure? Okay. Well, so Carrie, if I drop me and the elevator at the same time, we're going to go down the same amount of distance in the same period of time. So if I'm a foot above the floor in the elevator when the cable is cut, I'm going to go down a certain distance in a certain period of time, let's say 10 meters in, I don't know, 10 seconds. But the elevator's floor is also going to go down 10 meters in 10 seconds because we're all coming down together. Everybody, give me a thumbs up if that makes sense. Can I catch the floor? Can I catch the floor?
No.
Why?
Dr.
No.
Dr. Goldstein, can we do a time check?
Yes, I see that, but I've got to finish this.
Okay.
I need 5 more minutes.
Okay.
So if I'm going down a certain period of time in if I'm going down a certain distance in 10 seconds, the floor is going to go down the same distance in 10 seconds. And I'm asking, can I catch the floor?
You cannot catch the floor.
I can't, because every time I move towards it a certain distance, it moves away from me at the same distance. So what do I see in my elevator?
It looks like you're floating.
It looks like I'm floating a foot above the floor. I do this experiment over again and I look around, I said, who just turned gravity off? Gravity doesn't seem to be here anymore. I'm floating. I could push off this wall and float to one side. I could push off this wall and float to that side. I could push off the floor and float to the ceiling. What I've done here is kind of ironic, right? Because it is the force of gravity that's causing everything to plummet in free fall. But inside a freely falling laboratory, everything will behave as if gravity is turned completely off. Does everybody kind of feel what I just said? Okay, I know that's weird, right? But I can't catch the floor. Do I see the floors of the Empire State Building flying by me at an ever increasing speed? Do I see the floors going by?
No,
Why no?
because the door is closed.
The door's closed and there's no
Windows.
windows.
Oh,
I'm just seeing the same elevator I saw the first time, but this time gravity went away, apparently. Okay, it looked like gravity went away. So here's the last piece before we end. If there's no air in this room, and I drop this ping pong ball, is it in free fall?
yes.
Yes.
The only force acting on it is gravity. This is the elevator. What happens if I take this ball and I throw it with a little speed? When it leaves my fingers, is it in free fall? Is the only force, okay, I'm pushing it, right? I'm giving it a little push. And so I'm giving it a force, right? And that accelerates it up to a certain speed. It comes off of my fingers at a certain speed. But once it leaves my fingers, what is the only force acting on it if there's no air in this room?
Gravity.
Gravity. So once it leaves my fingers, is it in free fall?
Yes.
Yes. Can somebody tell me how it moves?
Parabolic.
It
Or
arcs
projectile.
and then it hits the ground. What if I throw it faster?
It goes farther.
It'll go farther and hit the ground. What if I keep throwing it faster and faster?
Keep
It will hit the
going
ground.
It'll
sideways.
go even farther before it hits the ground. And you know what? If I throw it really, really, really fast, as it arcs, the arc will be so large, it will swallow the earth. And in 90 minutes, I can catch it in my other hand. Right? If I throw it really fast, horizontally, as gravity causes it to fall, it will go completely around the earth. And in an hour and a half, I can catch it in my hand from the other direction. Ladies and gentlemen, this is the elevator. And this is the International Space Station. The International Space Station is the elevator. The International Space Station is in free fall. And the astronauts inside that freely falling laboratory will look weightless. Are they weightless? No, they're weighted, but they seem to have no gravity. And so the whole idea behind a microgravity experiment, to connect up from before, I wanted you to understand what's going on here. The astronauts are not weightless because they're far from the Earth. There's gravity in space. They are weightless because they're in free fall, just like that elevator. And so the whole idea behind a microgravity experiment is if you bring your experiment to the International Space Station, it will behave as if there's no gravity at all because it's in free fall. And Grace, what do I need?
Your control.
I need the same experiment on the ground operating in gravity. And when the flight experiment comes down and I put them side by side, this one operated in the seeming absence of gravity. This one operated in gravity. And I look for behavioral differences in what I'm studying to understand the role of gravity in the experiment. So summarizing this really, really fast, if you don't care about the force of gravity and how gravity works, if you don't care about why standing on my mountain I weigh 90% of what I weigh on the surface of the Earth, if you don't care that the astronauts are weightless because they're in free fall, okay. The point though is that, kind of short-circuiting this to the Monarch Note or the Cliff Note version of this story, if you bring something to the International Space Station, it will behave as if gravity's turned completely off. And if you run your experiment up there, you've changed the gravity variable, at least according to the experiment. And if you run the experiment down here on Earth and you get the flight experiment back and you look at them side by side, you can see behavioral differences to understand the role of gravity in what you're studying. Does everybody understand what a microgravity experiment is? It is classic experiment design. You want to change one variable. The variable you want to understand is the role of gravity in something. I can't change the gravity variable, so I trick the experiment. I put it in a continuously freely falling environment where it will behave as if gravity's turned completely off. Now, I know we went over, but I didn't want to stop in the middle of that story. So